Alright, hello everybody. In this segment we're going to be talking about rectangular components. In this case you can see I drew a vector represented by this F, and I'm on the XY coordinate system. The whole principle behind this is that if I were to look at a projection of this vector down onto the x-axis, what I could say is that I have a component of that vector, which we could call f sub x, and I can do the same thing with the y-axis, and that gives me a vector f sub y. Of course, this is all based on whatever angle theta I am from either the x or the y-axis. You can see that this forms a rectangle, and that's why we call these the rectangular components. We need to define what a unit vector is, and we're going to define this unit vector as a vector that has a unit magnitude along either the x-axis or y-axis, x-axis being I hat and y-axis being j hat. And if we have this unit vector, meaning a magnitude of 1, and it has a direction, either being along the x or y, now we can define our vectors, our unit vectors, as the unit vector fx with the magnitude of the force in the x direction times I hat. So basically the I hat is giving us the direction, the f sub x is the magnitude, and same idea with the y direction. So notice where I have the little the arrow above the letter indicating a vector in the beginning, that goes away because it's only magnitude when I put it into these unit vector directions. So my fx and fy are scalars, not vectors. Quick trig review. That's hard to say 3 times fast. If I had a vector that was located on this coordinate system, we have some vector f, and we know some angle theta, and we're interested in these rectangular coordinates. Well, I can see with this fy, I could put fy and just move it over to this other side and add it in essence head to tail. Well, that's basically what happens when we're looking at these components of these vectors. So in this case, looking at the projection straight down, I end up with some kind of vector in the x direction, my component in the x direction, and I have a component in the y direction. Now from trig, you might remember our vector in the x direction is equal to f times the cosine of theta. Notice that's all a scalar, so I'm going to put in my unit vector I hat, and same idea in the y, but now I have sine theta. So hopefully remember your SOHCAHTOAs, and you don't have to go back and say SOHCAHTOA every time, but instead you can identify what will be your cosine, or which component will be your cosine, which one will be your sine. Now, as far as this theta, and if you're going to automatically use cosine or sine, you're fine as long as this theta, this angle, is measured from this positive x-axis in the counterclockwise direction. So what this really means is if I'm rotating my axis, if that's say 30 degrees, I can plug it right in with my cosine 30 would give me my component in the x direction, my sine of 30 would give me the component in the y direction. However, if you're given an angle that is way over on the other side, you still have to resolve, and say you're given an angle from the y-axis, you still have to resolve that, either have to recalculate that angle all the way to the x-axis, or you need to look at this new angle, we could call it alpha, and instead in this case we would have components that would in essence flip. So my component in the x direction would be sine, and my component in the y direction would be cosine. Hopefully that kind of makes sense. If not, visit your trig functions, draw out your triangles, and refresh your memory on how all of that works. Let's go ahead and look at an example. Let's say that we want to define the x and y components of a particular force. In this case, it'll be of 150 Newton force, and so you can see what I'm talking about. Let's say that we have our coordinate axis, our x and our y, and this vector just happens to be coming off some angle over here. It's our 150 newtons, and it's at an angle of 35 degrees. So if you want to break this into its components, we have our same triangle, and this would be my fx component, that would be my y component. Then looking at our trig functions, what I prefer to do is I prefer to say, well, I know that if I take 150 times the cosine of this 35 degrees, what it would give me is this vector down here on the x-axis. However, I have to watch my signs because it is actually a negative vector. So I'm going to put in a negative right there. And I'm just adding it because I see which direction it's going. As an alternative, I could have found this angle, that angle being 180 minus 35, and then use the cosine of that angle, and the signs would take care of themselves. Either way will work. I just think this way is a little bit quicker. That's supposed to say f sub x. Looks a lot like a y. And if I do that, I end up with something like negative 122.9 newtons I hat. Same idea in the y direction. And I have to say, well, is that going to create a positive or negative y component? And I can see it's pointing up, so it's going to be a positive. No reason to change the sign. The other thing that I'm doing in my head is I'm looking at this angle. If it's from the x-axis, then I know cosine is my x component and sine is my y. If this angle were from the y-axis, if I were given that angle, I would flip those, and my x component would be the sine of my angle, and my y component would be the cosine. So in this case, I have a positive 150 times the sine of 35 j hat, giving me something like 86 even newtons. So that's about as easy they get, just resolving vectors. You should also know how to work backwards. If you're given the components, how do you find the magnitude and direction of your vector given just the components? So I'll call this working backwards. Don't ask me why I'm underlining a little bit. Writing, underlining, very odd. Weird mindset. So let's just look at an example to see how we would work backwards. It's pretty easy stuff. A little Pythagorean. Let's say that we are given a vector, and in this case we're given that some vector f has the components of minus 120 pounds in the I hat direction, minus 210 pounds in the j hat direction. If I were to draw it out, I should put what I'm going to find too. Let's go ahead and find the magnitude and the direction of the resultant vector. Should have said the force, not really the resultant. So if I were to look on a coordinate system and map out what this thing looks like, I put my components on here. In the x direction, what I'm saying is I'm going in the negative direction 120 units. So I'm going down over 120 pounds. And in the y, I'm going down negative 210 pounds. Notice I'm not putting the negative in front of those numbers because they are the direction is already indicated by the arrow, so I'm not putting on the number. And we already said it creates rectangular coordinates. You could also just draw them head to tail if you feel comfortable with that. This is actually what I'm saying is I'm trying to find this overall force vector and some kind of angle. So I have to designate where that angle is from. Well, I can see that this, if I move the 210 over, what I'm creating here is, because it's the same magnitude, same direction, I can move these vectors around. What I create is a right triangle, a 90-degree triangle. So from there I can use my Pythagorean theorem and find out that the magnitude of that force is equal to the square root of the squares, or 120 squared plus this 210 squared. And that gives me something like 241.9 pounds. As far as that angle theta, I could find that by taking the inverse tangent of the opposite over the adjacent, and that gives me an angle of like 60.3 degrees. So when it actually comes to problems like this, for my classes anyways, you're fine if you find the angle from any axis, but meaning the positive x, positive y, negative x, or positive x, whatever, but you need to designate where it's coming from. So in this case, I would write it as we have 241.9 pounds at an angle of 60.3 degrees, but I have to tell you where that's measured from. And so I'm going to draw a little sketch, and I can see that that must be measured from the negative x-axis and then pointing down. You could also do it from the positive x-axis or really anywhere else. I don't know why I suddenly have blue. Let's make that red. Groovy. The last thing we need to cover is how to add multiple vectors together using the x and y components. Last time we saw if we wanted to add two vectors together, in this case, let's say we wanted to add some vector A, and let's say we want to add to that some vector B. Last time what we did is we added them head to tail and we made this triangle. So we said, well, we're going to take, let's take A, and then we're going to add to it some vector B, and we end up with some resultant R. Well, the way we're going to think about this today, I guess I should label all this, this is A and B, is if I were on my coordinate axis, what I can do is I can actually look at how the projections would work, or the components would work. And for A, I see I have some kind of AX I hat, and over here I can add on to that. So this would be my vector for the x direction from vector A, and then I would have BX I hat. And same thing with the Y. I have an A Y J hat, and following B on over, I end up with a B Y J hat. So for this resultant, I can also see that if I add up my x's, I get my total resultant in the x. Add up my y's, I get my total resultant in the y. Or in essence, what I can say is my resultant force for the x component would be equal the resultant of, or the x component of vector A plus the x component of vector B plus however many you end up having, or as a fundamental equation, the resultant in the x is equal to the sum of all of the components in the x direction. Of course, same idea with the y. Alright, to keep these videos from being too long, I'm going to end it there, and I'm going to have a second presentation with an example on how to add these vectors together. So look for that in the YouTube channel, and thanks for listening.